Good day, everyone. This is the continuation of the design of structure in STAAD. Today, we're going to be applying loads to our structure. First, we're applying the wind loads. To do this, we're going to loadings, wind definitions, add, type number 1, comments wind X, and code ASCE 7 2010. Add, close. We're going to click on type 1 wind X, click add. On intensity, generate. And under common, we're going to be inputting our parameters. These parameters can be found in NSCP 2015. Building classification category can be found in Table 103, 1 occupancy category. Our occupancy category for this structure is category 3. Basic wind speed can be found in figure 207A.5 in NSCP 2015. Our basic wind speed is 270 kilometers per hour. Exposure category can be found in 207A.7.3. Our exposure category would be exposure B. Structure type is building structure. Consider wind speed up over hills or escarpment. Click no. Click apply. Under main building data, our building height would be 7.80725 meters. Our building length along the direction of wind, or L, is 36 meters. Our building length normal to the direction of wind, or B, would be 12.18 meters. Building natural frequency is 2.902413 Hertz. Building damping ratio is 0.05. Enclosure classification is enclosed. Check use KD. KD is 0.85. Apply. Under building design pressure, check windward. Check use G. Our G would be 0.85. Apply. Click OK. Add. Then close. Next, click wind definitions. Add. Wind type 2. Comment wind Z. Code 2010. Add. Close. Press type 2 wind Z. Click add. Under intensity, generate. The same as wind X. We're putting category 3. Basic wind speed 270 kilometers per hour. Exposure B. Building structures. And consider wind speed up over hills or escarpment. No. Click apply. Main building data. Building height is 7.8025 meters. Building length along the direction of wind is now 12.18 meters. Building length normal to the direction of wind, or B, is now 36 meters. Building natural frequency is the same as wind X, 2.902413. Building damping ratio is 0.05. Enclosure classification is enclosed. Check use KD. KD is 0.85. Apply. And under building design pressure, click windward. Use G. G is 0.85. Click apply. OK. Add. Then close. Now that we've input our wind definition, next let's input our seismic definitions. For this, we're going to loading. Under load and definition, click seismic definition, add. Under seismic parameters, type is UBC 1997. Do not check include accidental load. Our parameters can be found in NSCP 2015. Our zone is 0.4. Importance factor is 1. RWX is 8.5. RWZ is also 8.5. Soil type profile is 3. Near source factor is 1. Near source factor NV is also 1. Cte value 0.0731. Add, close. And now let's input our load cases. Let's close definitions, click load cases details, add, and here we can input our load cases such as seismic, dead load, live load, and wind loads. Now let's input our load cases. First, we're inputting seismic H, titled EX1, add, another seismic H, titled EX2, add, another one with title EZ1, another with EZ2. Next, we're inputting our dead load. Under loading type, click dead and input DL1. Another dead load for our superimposed load, titled DL2. Next, we're inputting our live load under loading type live, titled LL. Next, we're inputting another seismic H load, titled RSX. And another one with title RSZ. Next, we're inputting our wind load cases under loading type and wind, title WX, another with title WZ. Close. First, we're inputting our dead load. Click the L1, click add, and under self-weight load, direction Y, factor -1, click add. It will show up here. Click self-weight, assign to select, assign to view, then assign. Click yes. It will be assigned to the highlighted area, which is all the frames. Now we're inputting our floor loads. Click the L1, add, find floor loads, click group. Our pressure for all floors is negative 2.36. Input to second floor one way, click one way, add. It will show up here. Next would be 2F two-way, so we will uncheck one-way distribution, add. Next is third floor two-way, add. And next is 1F landing two-way, add. Then close. Here it shows up our floor loads. Now we're going to input our stair loads. Here, the stairs would start in this beam. Then the landing would be here, and the end of the stairs would be here. First, we're going to input the load of the stairs in this beam. Click the L1 under load definitions, add, member load, uniform force, and our computed W1 for our second floor is negative 16.298. D1, as you can see here, D1 is where the load will start, and D2 is the length of the load, or where the load will end. Here, the length of our beam here is 4, and the stairs is half of the beam. So if the load starts here and ends at the middle, the D1 would be 0 and the D2 D2 would be 2. Direction is global Y or GY. Click Add, and it will show up here. Close. Now click the load, negative 16.298. Use cursor to assign. Assign, and find the beam where the load would act, which is here. Oops. Let's fix the view properly. Oops. There. Now, the load of the stairs act at this beam where it is intended. Next is for the landing, which would act here. Let's click DL again, add, member load, and uniform force. The computed W1 is negative 3.6933. D2 and D1 would be 0 because it would act on the whole member. Global direction is DY. Click Add, close. We already clicked where the beam where the load would act is already highlighted. All we have to do is click the load, assign to selected beams, click Assign, click Yes. Now the blue arrows is the loads that is acting to our landing beam. Next, the load would act in this beam. Click the L1, add, the same as the other load. It is member load, uniform force, and W1 is negative 16.298. D1 would be 2 and D2 would be 4. Global direction Y, add, close. Click the load. The beam is already highlighted. Assign to selected beams. Assign, yes, there. The stair starts here. The landing beam is there, the blue arrows, and the end of the stairs is here. Next, there is a stairs inside one of the rooms. Let's check. Let's fix the view. Here, the stairs starts here and ends here. Now the load will act here. So let's input the stair loads there for proper viewing. The stairs will start here and ends here. But the stairs is small and would only act in this small small part. Click the beam where the stair load will act. Click DL, add, member load, uniform force. The computed W1 is negative 2.36. I mean negative 3.711, I should say. Negative 3.711. The D1 would be 0 and D2 would be 0.070 or 0.75, which is the width of the stairs. Global direction Y, add, close. Click the load and assign to selected beams. And assign, yes. And the small arrow there is the stairs. That is the stair loads. Next, we're going to input our superimposed loads. Superimposed loads will be put in DL2. And first, in our superimposed loads, we're going to input roof loads. Our roof loads will be the loads from the truss. The truss will act at the columns. The loads of the truss will act at here at the columns of the structure. Let's use the cursor here at the nodes. This is where the loads will act. Now, our truss spacing is 2 meters. This beam is 4 meters. So we need to input loads in the middle of this beam. So let's input our loads. For that, we're going to loadings, DL2, add nodal load because the load will act at the nodes. Under FY, the computed load of our truss is negative 5.620. Oops, that is 5.620. Add, it will show up here. Next, this load will apply here. Let's isolate these roof beams. This negative 5.62 will act here, will be put here in this node. Next is the loads that will be put here. So let's do it again. DL2, add nodal load, and its load is negative 7.371. Add. Next, it is at the middle column, and the calculated load is negative 15.491. Add. Next is negative 7.709. Oops. Add. Now let's assign our loads. To make it easier, we're going to side view. As stated earlier, this load will act here. So let's highlight these nodes. If you highlight it using click drag method, the other nodes will be selected as well. Let's go to side view. Click the load, assign to selected nodes, then assign yes. The arrow represents the loads. The arrow is too big, so let's try yes, there it is. Now, next for this load, we'll highlight this group of beams, nodes. Click the load, assign to selected nodes, and assign yes. It's do the same for the other nodes. Next, we'll input the loads on the members. Let's do the same. Add. Now it will go to member load. Concentrated force. P is the same, negative 5.62. 5.62. The same as here, 5.62. As you can see here in this illustration, you can see how far from the start the load will act. Let's put 2 because that is where the middle of the beam would be. Add and do the same for the others. Negative 7.371. 2. Add global direction wise. Oops, that is wrong. That's supposed to be negative. You can click it, edit, and change P into negative. Modify, and there it goes. Member load, concentrated force, same, negative 15.491. D1 is 2, add, it's negative 7.709. Add. So to make it easier, we're going to side view. Use beam cursors and select the beams here. It would select all the beams. Now assign the negative 5.62 here. Assign to selected beams. Assign. Yes. And as you can see, now the spacing of the loads is 2. From the node to the middle of the beam to the other node, all the spacings would be 2 meters. Now let's do it to the other beams. You can see here, all the stress is now acting to the beams and the columns. Click display whole structure, and there is the roof loads. Now to make it more organized, we're going to command file and add comments to the loads. Let's find where the load is. Here at one-way load, let's put asterisk floor loads. Putting asterisk at the front of the word makes it a comment, so it will not affect your commands. Stair loads. Oops. Here we have roof loads. Save your work once in a while. What the fuck? What the fuck is that? Now next we're inputting our wall loads. Let's go to DL2, add member load, uniform force. Here in W1, our computed exterior wall load is negative 9.238. GUI, add, and close. And this load will act at the second floor beams. So let's isolate the second floor beams. Now let's input our loads to where the walls are. First, let's highlight all the beams where the walls are. Now we're going to input our now we're going to input our second floor wall loads. Let's isolate the second floor. These beams is where the wall loads will be assigned. Let's add the loads for our beams. Click DL2, add, member load, uniform force. And the computed wall load for our walls is negative 9.238. Add. This load is the load of walls that have a height of 3.1, which is here, here, all of the walls around here. Now that the beams are highlighted, let's input our wall loads. Assign to selected beams, assign, yes. Next, we're going to add the loads for the walls here and here. Because they have different height, of course, they have different loads. Now we're going to input the wall loads for here and here. The height of the wall here is 2.02, and the computed dead load of its wall is negative 6.0196. Add, and we're going to apply it here. Assign to selected beams, assign yes. Next is the wall loads for here, and the height of this is 1.08, and the computed dead load of its wall is negative 3.2184. Add, close, and assign it to these beams. There. Next is the loads for our first floor. Let's display whole structure and isolate the loads for our the beams for our first floor. Select beams. Now the height is the same as the second floor. I'm sorry, it's not. The height of the first floor is 3.84, which has a computed dead load of negative 11.443. Add, close, and assign it to the to where the wall is. Assign to selected beams, assign yes. There. Next is the dead load for these beams, which has a height of 2.18. The calculated dead load for its walls is negative 6.4964. Add and assign. Yes. Next is the load for here. Let's show the whole structure and isolate. So we have a better view. It would be here, 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 and here. There. That's a height of 1.66, I believe. Yes. Let's highlight it again. And the calculated dead load for its wall is negative 4.9468. Add, close, uh, assign to selected beams. Yes. Table structure, and let's find if there's are still ones that we forgot. Mm, I believe we have a miss input here. So we're just going to edit. The beam number is 1031, which is here, and we're just going to remove it. Assign, yes, and it gets removed because the height of this is actually 1.66 plus 1.08, and the computed dead load of it is supposed to be negative 8.1652. Add, close, and this we'll just use cursor to assign and click on. There it is. Now that is the dead load for our superimposed dead load for our walls. Now next, we're going to input our design spectrum. The span spectrum curve is already made before. This can be found in the values of this can be found in NSCP 2015, like this table 2087 in NSCP and table 208-8 for finding CV and CA. This response spectrum curve can be found in this 2083. Next, we're going to input our design spectrum curve. This is the response spectrum curve. This is already made before by me. The value of this can be found in NSCP 2015, like this. At NSCP 2015 table 28-7, you can find the value of CV, and table 28-8, you can find the value of CA. This response spectrum curve can be found in figure 208-3. And the thing that we need here is this, which is the period and the acceleration. This is what we're going to be using for our STAAD. So let's go back to STAAD, and under loadings, load case details, let's press RSX, add, find response spectra. Under response spectrum, code is custom, combination method is CQC, tick acceleration, linear, and damping. Check direction, and the value of x is 1/8.5, which is 0.11765. And next, we're going to check damping, and the damping is 0.05, which is already here, and the scale is 9.81. And more and add. Oh yes, but we're going to paste our period and acceleration here, which is this, which is already highlighted. So let's copy it, Control C, and paste it here, Control V. There are 39 lines and ends at 8 and 0.08. Let's check. Yes. And now we're going to add. Shows up there. Oops. Add is wrong. So we're going to remove this. Press this and delete. Let's do the same to RSZ. So add, find response spectra, custom, code is custom, combination method is CQC, acceleration yes. This is RSZ, so let's check Z, and the value is 0.11, 0.11765. Let's also paste the spectra here. Scale is 9.81. And add, close. Next is for our wind load. Press WX, add, find wind load, select type regular, tick X, windward pace, and factors 1, add, close. Next is WZ, add, find wind load, select type 2 regular, and press Z windward pace, add, close. There's our spectrum and our wind load. Next, we're going to analysis and design. Find miscellaneous command. Press cut off mode shape. Maximum number of mode shape is 20. And add. Press OK. And there. Now in our utilities, click command file, save, and go to the very bottom of the command file. Find finish, and before finish, type perform analysis, which can be found here. There, from analysis. Save your work once in a while. Press X, and wait for it to load. There, analysis and design. Run analysis to look for errors. And there would be one error. You have view output file, done. And let's find the error, which says no reference load cases. No reference load cases. This could be easily fixed by going to command file and looking for the reference loads. There, starts at define reference loads. We're going to highlight it, and until the end of reference loads, press Ctrl X and remove this extra space and put the reference loads just after member of set, which is here. Enter Ctrl V and save your work. Press X and let's wait for it. No error so far. Oops. Now analysis and design. Run analysis and let's see. No errors. One warning, 8 notes. View output files, and this warning is okay, and these notes are not that much. It's just notes and warnings. It's not an error, so our structure is okay. And that's it for our part 2.